The very first function is single-sided exponential curve. So this is a single-sided exponential curve. As the name suggests, single-sided means it exists only one side of the axis. Exponential curve, that means this curve is exponentially either increasing or decreasing. So this is a exponentially decreasing curve. So it is a negative curve. So we can define it by e raised to the power minus at. So the formula for Fourier transform, you know that f of omega is equals to minus infinity to infinity ft e raised to the power minus j omega t dt. So now this formula can be divided into two parts. The limit can be divided from minus infinity to 0 and 0 to infinity. Rest of the formula will remain same. So now from minus infinity to 0, that means this negative side. What is the function? It is nothing but 0. So in place of ft we will write 0. So this function will not exist. Only existing part is from 0 to infinity. So from 0 to infinity, what is the function ft? It is e raised to the power minus at. So in place of ft we will write e raised to the power minus at. So this will become 0 to infinity e raised to the power minus at e raised to the power minus j omega t dt. Both these exponential curve can be combined. So it will become e raised to the power minus of a plus j omega t dt. Now if we integrate this term, it will become e raised to the power minus of a plus j omega t upon minus of a plus j omega with the limit 0 to infinity. Now we will put the limit. So it will become e raised to the power minus infinity minus e raised to the power 0. E raised to the power minus infinity can be write as 1 upon e raised to the power infinity, which will be 0, and e raised to the power 0 is 1. So 0 minus 1 is minus 1 upon minus of a plus j omega. This minus and minus will become cancelled. So this will become 1 upon a plus j omega. So your Fourier transform f of omega is nothing but 1 upon a plus j omega. Now every Fourier transform is having two components. One is known as its magnitude, which can be defined by mod of f omega, and another is the phase, which is defined by theta omega. This theta omega is nothing but tan inverse of imaginary part upon real part. So this mod of f omega is basically calculated by this 1 upon a plus j omega. This j is the imaginary term. So it can be calculated by 1 upon under root of a square plus omega square. This way you calculated the magnitude in mathematics also previously. Now we will see how you can calculate the phase. So to calculate the phase, we will rationalize 1 upon a plus j omega. So for rationalization, we will multiply this term by a minus j omega. So this will become a minus j omega upon a plus b into a minus b will be a square minus b square. So a square minus j square omega square, and j square is equals to minus 1. So minus and minus will become plus. So this will become a minus j omega upon a square plus omega square. So the real part of this is a upon a square plus omega square, and imaginary part of this is minus of omega upon a square plus omega square. A upon this is the real part, minus of omega upon this is the imaginary part. So this way we can calculate that theta, which is tan inverse of imaginary part upon real part. Imaginary part is minus omega upon a square plus omega square, and real part is a upon a square plus omega square. This a square plus omega square will get cancelled, and you will get minus of omega by a. This minus tan minus theta is minus tan theta, so this minus sign can be written in front of this tan, so it will become minus of tan inverse omega by a. So now if we want to plot the graph of this graph is time domain graph. Now we will plot the frequency domain plot. Frequency domain plot means in the x-axis you are having omega, and in the y-axis you are having f of omega. That is the Fourier transform or the function in frequency domain. So first we will calculate the magnitude. If we put omega is equals to 0, it will become 1 upon root a square, which is 1 by a. So that means at omega is equal to 0, it will be 1 by a. And as you increase the value of omega, the value will decrease. If you put omega is equal to 1, it will be a square plus 1 root. And if you put omega is equal to minus 1, it will also give the same value, because square of plus and minus both values are same. So that way it will be reducing at both ends, in negative as well as positive side. So this is the maximum value, and then it will start decreasing in both directions. So this way you can plot the magnitude of this Fourier transform of single-sided exponential curve. Now we will draw the phase. So for phase we will take three angles, 0, 90 degree and minus 90 degree. Tan 0 is 0, so at tan 0 it is 0. Tan pi by 2 is infinity, but it is having negative sign, so that means for pi by 2 it will be minus infinity, and for minus pi by 2 it will be plus infinity. So at minus pi by 2 it is giving minus infinity, and it is pi by 2 it is giving minus infinity. So plot will be something like this. It starts from infinite positive side and it will go to the negative side. So this way you can draw a tentative phase plot of the Fourier transform of single-sided exponential curve. So if in the exam they will ask calculate the Fourier transform of single-sided exponential curve, so you have to calculate the Fourier transform, then its magnitude, its phase, and then you have to plot the spectrum also. If you solve till this end, you will get the full marks if they ask the Fourier transform of single-sided exponential curve. So I hope you understand the concept of single-sided exponential curve and how you can calculate the Fourier transform of any given function. Double-sided exponential curve and its Fourier transform. So as the name suggests, double-sided exponential curve, that means an exponential curve which exists on the both sides of the axis. So it is existing at the positive side as well as at the negative side. This part we have already covered this in the single-sided exponential curve, which was e to the power minus 80 because it is a negatively exponential curve. Similarly, this is also a negative exponential curve, so it will be e to the power minus of a, but here t is also negative, so minus a into minus t, that is why I have kept it e to the power at, but basically it is e to the power minus a into minus t. So this part is e to the power 80 and this part is e to the power minus 80. In the single-sided exponential curve, we have kept the limit from minus infinity to 0 as 0 because this part was nothing but 0. So in this case, as the Fourier transform f omega is minus infinity to infinity ft e to the power minus j omega t dt, we will divide the limit or break the limit into two parts, which is from minus infinity to 0 and 0 to infinity. So from minus infinity to 0, your function ft is nothing but e to the power 80. So I have written e to the power 80, then e to the power minus j omega t dt. So this is the complete section between the limit minus infinity to 0. Similarly, from 0 to infinity, this part we have already covered in the single-sided exponential curve. So this part I have not emphasis much because we have already calculated this part and the result was 1 upon a plus j omega. So I have directly written 1 upon a plus j omega. So we will concentrate on minus infinity to 0. So from minus infinity to 0, your function is e to the power 80 e to the power minus j omega t dt. We will combine this exponential term. It will become e to the power minus of a minus j omega t dt. So by integrating this, e to the power a minus j omega t upon a minus j omega, with the limits minus infinity to 0. When you put e to the power 0 upper limit and then e to the power minus infinity lower limit, e to the power 0 is 1 and e to the power minus infinity is 0. So 1 minus 0, that is 1 upon a minus j omega. So overall you will get 1 upon a minus j omega for the first part and 1 upon a plus j omega for the second part. So by solving this, take the LCM, which is a plus j omega and a minus j omega, that is a minus b into a plus b, which comes out to be a square minus b square. So this is a square minus b square, and j square is minus 1, so it will become a square plus omega square. And then in the numerator part, it will be a plus j omega here, and then a minus j omega and minus j omega will get cancelled. You will get 2a upon a square plus omega square. So as you can see, the result 2a upon a square plus omega square does not contain any imaginary term. because there is no j in this particular solution. So we can say that our phase is 0 because there is no imaginary part, because phase is what? Theta is equal to tan inverse of imaginary part upon real part, and then imaginary part is 0, so overall phase is 0. And what is the magnitude? This is nothing but the magnitude. If there is component of imaginary section, that is j, then we have to take it as mod of f omega, but this is nothing but the overall magnitude. So now we can plot this against the frequency. This is omega and this is f of omega. When you put omega is equal to 0, you will get 2a upon a square, that is a and a get cancelled, 2 by a, so the maximum value is 2 by a. Then you can keep on increasing the value of omega in both the direction. Put omega is equal to 1, omega is equal to -1, the value will decrease somewhat. Then increase the value of omega, the value starts decreasing in this manner symmetrically, because for both omega positive and negative value, the value remain equal. So it will start decreasing in both the direction. This is what the magnitude spectrum. Obviously the phase is 0, so there is no phase plot. This is what the Fourier transform of double-sided exponential curve. This is the diagram, or you can say pictorial representation of gate function. Gate function is nothing but a rectangular pulse of a specified width and height. As you can see in this diagram, the width of this pulse is tau and height of this pulse is a. So this is a predefined function, gate function. Now we will calculate the Fourier transform of this gate function. So first of all, we will define this function f of t. As you can see, between minus infinity to minus tau by 2, the function is 0 because it is not existing, and from tau by 2 to infinity, this function is also not existing, so also that is 0. So this function is only existing between this limit, and in this limit the value of the function is a. So we can define our function ft is equal to 0 between the limit minus infinity to minus tau by 2, a minus tau by 2 to plus tau by 2, and 0 tau by 2 to infinity. So this is the function ft. Now we will calculate the Fourier transform of this ft. The formula for Fourier transform you already know. It is integration over the limit minus infinity to infinity ft e to the power minus j omega t dt. So in place of ft we will write this a within the limit minus tau by 2 to plus tau by 2. So this f omega will become minus tau by 2 to plus tau by 2 ft e to the power minus j omega t, where ft is a. Now we will integrate this. E to the power minus j omega t will be integrated and will give as e to the power minus j omega t upon minus j omega. So this is what the integrated section, and the limit minus tau by 2 to plus tau by 2. Now we will put the limit minus tau by 2 to plus tau by 2. A by minus j omega, that is minus a by j omega, we have kept outside the bracket, and inside the bracket e to the power minus j omega t. In this t we will put the limit. First is tau by 2, second is minus tau by 2. So minus tau by 2, and this minus sign will become plus, so this will be e to the power minus j omega tau by 2, and this is e to the power plus j omega tau by 2. Now this minus sign I will take inside the bracket, so it will become a by j omega. This quantity will come here and this quantity will come here, or you can say this will become positive and this will become negative. So I have written is like that. Now I have multiplied and divided this particular value with 2. So this will be 2a by omega, and 2j I have kept inside the bracket. I have done nothing. I have just multiplied the numerator and denominator with 2, and then 2j I have kept inside the bracket, and 2a by omega I have kept outside the bracket. Why I have done this? Because you know this trigonometric identity which says that sine theta is equal to e to the power j theta minus e to the power minus j theta upon 2j. So this is e to the power j theta minus e to the power minus j theta upon 2j, where theta is nothing but omega j by 2. So if something is like this, e to the power j theta minus e to the power minus j theta by 2j, it will become sine theta. So in place of theta, whatever quantity is there, it will be becoming the sine factor. So it is now sine omega tau by 2, 2a by omega. So this is the solution. Now we will further solve this thing. Otherwise, this is also you can write in the exam till this point you can also calculate the Fourier transform. This is nothing but the Fourier transform of gate function. So now further what I have done, I have multiplied and divide this quantity with tau by 2. So it will be 2a into tau by 2 upon omega tau by 2 into sine omega tau by 2. Now 2 and 2 cancel, so it will become a tau sine omega tau by 2 upon omega tau by 2. And then I have written a tau sampling of omega tau by 2. This is another function which is known as sampling function. Sampling function is nothing but it is sin t upon t. If you have a quantity like sin t upon t, then you can write it in the form of sampling function. And the graphical representation of sampling function is this. It will give the maximum value at 0 and then it will start decreasing from at both ends. So this is nothing but a sampling function. In future we will also discuss something more about sampling function. For gate function, this much is sufficient, that sin t upon t is nothing but sampling of t. So this is sine, this bracket quantity can be considered as t, and denominator is also t. So this will be sampling of t, which is omega tau by 2. So this is a tau sampling of omega tau by 2. So this is what the Fourier transform of gate function, a tau sampling of omega tau by 2. So this is how you have to calculate the Fourier transform of gate function. Now in the exam, there are many modifications of this gate function. Suppose they may ask in the exam that a rectangular pulse is given whose width is 2 and it is specified from -1 to +1. So easily you can say that the width of this is tau. So here the width is what? Tau is equals to 2, and a is what? The height, which is also 2. So in this particular solution, if you put a is equal to tau and tau is equal, a is equal to 2 and tau is equal to 2, so you will get 2 into 2 sampling of omega 2 upon 2. So it will be 4 sampling of omega. So this is the solution for this particular rectangular pulse having width 2 and height 2. Okay, so instead of tau by 2 and a, they may give any value in the examination. So accordingly you can calculate the value. Next function is an impulse function. Impulse function graphically is represented by something like this, which exists only at t is equals to 0. And mathematically we can write it in this way: delta t is equals to 1 for t is equal to 0 and it is 0 otherwise. That means except for t is equal to 0, it will give the value 0 in all the values of t. So the formula for Fourier transform f omega is equals to -infinity to infinity f of t e to the power minus j omega t dt. Instead of ft, I have write delta t because you are calculating the Fourier transform of impulse function. So delta t is equals to 1 when t is equals to 0, as per the definition of impulse function. So delta t will be 1 and e raised to the power j omega t, and t is equals to 0, so it means e to the power 0, and e to the power 0 is also 1. So 1 into 1 is 1. So that means within that limit, that means from -infinity to infinity, this function only exists at t is equals to 0. So at t is equals to 0, you can write here t is equals to 0. At t is equals to 0 only this function exists. So at t is equals to 0, the function will give the value as 1. So the Fourier transform of impulse function is equals to 1. So it's a very simple function, impulse function, which gives the Fourier transform as 1. One more thing, one more function, sampling function, which we have already discussed in the previous gate function. Now you can see there are various sampling function I have drawn. These are 3 sampling functions you can see. This is a sampling function, another one, this is also a sampling function, this is also a sampling function. So this peak you can see where it is changing. This peak is low, width is more. As the width go on decreasing, this height becomes more. So there will be a condition when the width becomes 0, the height will be infinity. So this function will be something like this. You can see this is nothing but the impulse function. So that means sampling function can be related with the impulse function with some limits. What limits? If the limit tends to infinity, this sampling function can become the impulse function. The area of the sampling curve will always remains constant. It can be defined mathematically by integration k by pi sampling of kt dt is equals to constant, where this k by pi sampling of kt dt is the area of the sampling curve. So this area of the sampling curve will always remain constant. How it will remain constant? Because if the width decreases, height increases. If the height decreases, width increases, because you need to keep the area under the sampling curve always a constant value. So there will be a certain limit when this is your k3, this is your k2, this is your k1. That means height is basically denoted by different values of k. There will be a time where this k tends to infinite. Then k by pi sampling of kt will become delta t. As we have already discussed, if this width becomes 0, the height becomes infinite and it will only exist at t is equal to 0. And if this sampling function only exists at t is equal to 0, it will be nothing but the impulse function. So we can write it in this way: limit k tends to infinity, k by pi sampling of kt is equals to delta t. So this relationship please keep in mind, because it will be useful in various calculations of Fourier transforms. So this is an important result, or you can say this is an important relationship or an equation which will be useful further in various examples. So you just note down it in your notebook and keep a star mark, because this is an important equation. Next function is constant a. Constant a means it will give a constant value from minus infinity to plus infinity. It is an infinite function, but the condition for existence of Fourier transform is that the function should be finite. So we need to keep this function finite. So what we can do is we can project this function to this point in the x-axis at the point minus tau by 2 and plus tau by 2. So you can see this dotted part is nothing but a gate function, rectangular gate pulse, the Fourier transform for which we have already calculated. Now this function can also be defined as, if this is a constant a, so then constant a can be written as limit tau by 2 tends to infinity g of t, that is gate function. That means if gate function's limit is extended to infinity, this gate function will become constant a. So that means Fourier transform of constant a is nothing but Fourier transform of gate function with the limit tau by 2 tends to infinity. So we already know the Fourier transform of gate function, which is a tau sampling of omega tau by 2 with the limits tau by 2 tends to infinity. Now we just have discussed about the sampling curve and the formula. So we are writing this formula, which is limit k tends to infinity, k by pi sampling of kt is equals to delta t. So we will modify our relationship, because this k is equivalent to tau by 2. So we need tau by 2 here. So what we will do, we will multiply and divide with 2. So this tau by 2 is nothing but k. You need pi at the denominator, so I have multiplied and divided with pi. So actually I have multiplied with 2 pi here and 2 pi here. So this will now be comparable. This is k upon pi sampling of k, which is tau by 2, and t, which is omega. So if this is t, this is become delta t, but here t is replaced with omega, so it will be delta omega. What are the remaining things? 2 pi and a. So this is 2 pi a delta omega. So that means Fourier transform of constant a is 2 pi a delta omega. So this way you can calculate the Fourier transform of any number or any constant value. So if I will say calculate the Fourier transform of 1, that means constant value 1. So just put 1 in place of a. So it will become 2 pi delta omega. This will be the Fourier transform of any constant number. So this is generalized constant a, the result of which or the Fourier transform of which is 2 pi a delta omega. Now instead of a you can write any number and can get the Fourier transform of that particular number. So if I write 1 in place of a, the Fourier transform is 2 pi delta omega. So remember this thing, Fourier transform of any constant is 2 pi a delta omega. This way you can calculate the Fourier transform of any constant. Next function is a Signum function. Signum function is basically combination of two unit step function. Unit step function is mathematically defined by ut is equal to 1 for t is greater than or equal to 0 and it is 0 otherwise. So basically unit step function gives the value 1 for t is greater than or equal to 0 and below t is equal to 0 it gives the value as 0. That means on the negative side it gives the value 0 and in the positive side it gives the value as 1. That is called a unit step function. So Signum function is basically combination of two unit step functions. So Signum t can be defined as ut minus u of minus t. This section is a negative section, so this is minus of ut, and here t is also negative and the amplitude is also negative, so both the signs are negative. T is also negative, this is also negative. So Signum t can be defined as ut minus u of minus t. But you don't know the Fourier transform of ut, so you cannot directly calculate the Signum function's Fourier transform. So to calculate the Fourier transform of Signum function, we somewhat modify the Signum function in this manner. How? You can see these dotted lines. We have already calculated the Fourier transform of exponential curve. So this is nothing but e to the power minus at. What we can do is we can just put the limit a tends to 0. So this is e to the power minus at ut with the limits a tends to 0. Similarly, this is the negative part, so it will be e to the power at u of minus t with the limits a tends to 0. So this ut can be now modified, limit a tends to 0, e to the power minus at ut minus e to the power plus at u of minus t, both with the limits a tends to 0. So now this part is basically the limit 0 to infinity and this part is basically limit minus infinity to 0. So the formula for the Fourier transform exists for the limit minus infinity to plus infinity. So from minus infinity to 0 your function is e to the power at u of minus t e to the power minus j omega t dt, and for 0 to infinity your function exists e to the power minus at ut e to the power minus j omega t dt. So already we have calculated this part, minus infinity to 0, this part is 1 upon a minus j omega with a negative sign because in this the sign is negative, and this part is already 1 upon a plus j omega. We have already calculated this in the single-sided exponential curve as well as in the double-sided exponential curve. So I am not calculating all the things again and again because you have already watched the video previously and calculated these things. So this integration gives the result as 1 upon a plus j omega, and this integration gives the result 1 upon a minus j omega, this negative sign because of this negative sign. So when you calculate this, the denominator will be a plus b, a minus b, that is a square minus b square, a square minus j square omega square, and j square gives the value as minus 1. So that is why it is a square plus omega square. In the numerator it is minus a minus j omega, because minus will be multiplied with both these things, and this will be a minus j omega. So minus a and plus a will get cancelled and you will get minus 2 j omega upon a square plus omega square. Till now we are keeping the limit a tends to 0, Now we will put the value a is equals to 0. So this a square will become 0 and the remaining thing is minus 2j omega upon omega square. 1 omega will get cancelled. So we will get minus 2j upon omega. If you multiply and divide with j, this will become j square and j square gives the value as minus 1. So minus minus will become plus. So the numerator will become 2 and the denominator will become j omega. So either you can write minus 2j by omega or you can write 2 by j omega. So this is the Fourier transform of Signum function. As the Signum function cannot be calculated directly because Signum function is related to unit step function, you have to go through some different process and calculate the Fourier transform as 2 by j omega. This is what the Fourier transform of Signum function. Next function is unit step function. Unit step function graphically can be defined by a straight line which is existing from 0 to infinity, and it gives the value as 1 throughout. And mathematically you can define unit step function as ut is equals to 1 for t is greater than or equal to 0 and it is 0 otherwise. Again, we cannot directly calculate the unit step function, but we know the relationship between signum function and unit step function, which is signum t is equal to ut minus u of minus t. So from this relationship we will get the relationship of ut. Now see these graphs. This is a constant 1, this is a ut, unit step function, this is u of minus t. So what if I will subtract from 1 ut, I will get u of minus t. So that means I can write u of minus t is nothing but 1 minus ut. Again you can see that this is 1. If I subtract from this 1 ut, this part, what I will get? U of minus t. So that means u of minus t is nothing but 1 minus ut. So in this formula, instead of u of minus t, what I can write? 1 minus ut. So by solving this, you will get 2 ut minus 1, which can be written as ut is equals to 1 plus signum t by 2. This 1 will go there and 2 will be coming to the denominator, or you can write it as 1 by 2 plus 1 by 2 signum t. Now the Fourier transform of ut is nothing but Fourier transform of 1 by 2 plus 1 by 2 Fourier transform of signum t. You have already calculated the Fourier transform of constant, which is 2 pi a delta omega, and instead of a I will put 1 by 2, so that 2 and 2 will get cancelled, so it will be pi delta omega. For your reference, I will write Fourier transform of a is 2 pi a delta omega. Now instead of a, if you write 1 by 2, 2 and 2 will get cancelled, the remaining part is pi delta omega. So this is the Fourier transform of constant 1 by 2 plus 1 by 2 signum t Fourier transform you just have calculated, which is 2 by j omega. So this 2 and this 2 will also get cancelled. So the final answer is pi del omega plus 1 by j omega. This is the Fourier transform of unit step function. I hope you understand the calculation and the Fourier transform of unit step function.